All right, so today we're going to do something kind of fun. We're taking what looks like a really intimidating linear algebra exam, and we're going to crack it open. Because, it's not just a test. It's really more like a treasure map, and it points to some of the most powerful and honestly beautiful ideas in all of math. Okay, let's just dive right in.
So you might be thinking, it's just a bunch of numbers and brackets, right? But it's so much more than that. These problems, they're designed to test a way deeper understanding. Things like how systems actually change, what their fundamental limits are, and what their true nature is, deep down. So what secrets are we actually unlocking today?
Okay, first up, we're diving into one of the most central ideas in this entire field. It's all about the difference between an abstract action and the concrete tool we use to calculate it. It's about transformations and, you could say, all the different masks they can wear.
So at its heart, a linear transformation is just a fancy name for a rule. A rule that takes a vector, and you can just picture an arrow pointing from the center of a graph, and it does something to it. It might rotate it or stretch it out, or maybe even flatten it onto a line. The key thing to remember is that it's the idea of the action itself.
So how do we make that abstract idea actually work? Well, we use a tool called a matrix. But here's the really crucial point, and you can see it on the slide. A matrix is just a costume. It's a disguise. The very same transformation can wear a ton of different matrix costumes, and it all just depends on your point of view, what mathematicians call a basis. It's kind of like choosing to measure something in inches or in centimeters. The object itself doesn't change, but the numbers you use to describe it do.
And this is where it gets really interesting. The exam shows us that you can have two matrices that are what's called row equivalent. Basically, you can get from one to the other with a few simple steps. So they look really similar, right? They even share the same null zone or kernel. But, and this is the kicker, they can have completely different reachable worlds or images. So they might look alike, but deep down they're doing fundamentally different jobs.
Which brings us perfectly to our next big idea. If these transformations are actions, what are their defining features? What's hiding under the hood? To find out, we need to look at two really special spaces that are tied to every single transformation. And here they are, the kernel and the image. The kernel is basically everything that gets squashed flat down to the zero vector, the origin point. Think of it as all the inputs that just get completely erased by the transformation. The image, on the other hand, is the total opposite. It's the entire universe of possible outputs. It's everywhere the transformation can possibly take. Now for a really cool puzzle, pulled straight from this exam. We know what the kernel is for a single transformation, t. But what happens to that null zone if you apply the exact same transformation a second time? Does it stay the same size? Does it shrink? Or does it grow? So this slide walks us through the logic like it's a little story. The exam sets up a special case where we find this clever vector, let's call it u. Now, when we apply our transformation t to u, it survives. It doesn't go to zero. But, and here's the twist, the result, this new vector, t of u, has a special property. It is in the original kernel. So when we apply t a second time, it gets squashed to zero. So just look at what happened there. The original vector u wasn't in the kernel of t, but it is in the kernel of t applied twice, t squared. And that's the whole point. The null zone got big. Okay, so we've seen that matrices are costumes, and that transformations have these hidden structures. Now, for our final act, we're going to uncover the essential DNA of a matrix, the thing that really defines its ultimate behavior. Question 5 in the exam introduces us to this really special kind of matrix. It's called a nilpotent matrix, and it has this one wild property. If you apply its transformation over and over and over again, let's say k times, everything, and I mean everything, gets sent to the zero vector. It all vanishes. You could almost picture it, right? It's like a system that is doomed to collapse. Every time you apply the matrix A, the space gets squeezed and shifted and twisted until finally, after k steps, the entire space has just collapsed into a single point, the origin. It's a transformation that, at the end of the day, annihilates everything it touches. So, that leads to a really deep question. You see, every matrix has these special directions. They're called eigenvectors, and along these directions, its action is just simple scaling. That scaling factor is called an eigenvalue. So, for a matrix that eventually destroys everything, what do you think that fundamental scaling factor has to be? It can only be zero. I mean, think about it. If there was even one direction where the matrix scaled vectors by some non-zero number, you can never guarantee that those vectors would end up at the origin. The only way for this total collapse to be absolutely inevitable is if the core scaling factor is just zero. And the mass behind it is, well,
It's just beautiful. It confirms our intuition so simply. If a vector v gets scaled by a factor lambda, then applying the matrix k times scales it by lambda to the power of k. But we already know that applying the matrix k times sends every vector to 0. So the only way this equation can possibly be true is if lambda itself is 0. It has to be.
And this leads us to one last, really profound insight from the exam. See, a simple matrix can be completely understood just by its scaling behavior, but our collapsing matrix, it can't. Its only eigenvalue is 0, but it isn't the zero matrix itself. And what that means is that its action is way more complex than just simple scaling. It also shears and twists the space in ways that you just can't neatly separate or simplify. And that's what it means to be non-diagonizable. Its true nature is this complex, messy mix of actions, not just a simple stretch.
So, let's just take a step back and connect all these threads. We've kind of journeyed through 3 distinct, but actually deeply related ideas, and they were all just hiding in the pages of this one exam. So first, we saw that the matrix we write down is really just a disguise for a bigger abstract idea. Second, we uncovered those hidden structures, the kernel and the image, that really define a transformation's power and its limits. And finally, we decoded the true nature, the DNA of a matrix through its eigenvalues, and that revealed its ultimate destiny.
And here's why any of this really matters. These concepts aren't just abstract puzzles for a test. Understanding how a system changes, what its null zones are, and what its fundamental scaling factors are, that is the basis for how we model the real world. We're talking everything from the physics of subatomic particles to the algorithms that rank web pages on Google and pretty much power our entire digital lives.
It just goes to show you that right beneath the surface of all these formulas and equations, there's this incredibly rich world of ideas. So the final question is, if we can find all of this hiding in just a few problems on one test, what other incredible secrets are just waiting out there to be unlocked in the language of mathematics? Thanks so much for tuning in.